Ladies and gentlemen, welcome. We are looking at chapter 17 today. This is our last chapter in the probability section. It's called probability models, and we are now going to take what we kind of learned about probability here, and we're going to look at these in terms of a larger model, a very specific type of model. We are looking here mainly at this chapter to transition to inference. Inference being what we spend the last 3 months of this course on, from January to March. Basically, when we get back from break, we start talking about inference, and we talk about it for 3 months. Okay, this chapter is an essential chapter towards making that transition. Okay, so we're going to be talking about probability models. Specifically, we're talking about a geometric model. We are talking about a binomial model. And then finally, we're going to go back to our old friend, the normal model, because we haven't talked to our old friend, the normal model, in a long time. And we're going to see how these two kind of relate to the normal model, and then how the normal model ultimately relates to the idea of inference. Okay, so big chapter, very transitional to making towards understanding the stuff that we're going to be doing for the last sort of third of the class. So the first thing that we need to understand before we can talk about these two types of models are these things called Bernoulli trials. Okay, Bernoulli was a mathematician. He was sort of one of the instrumental people when we talk about probability. All of the models in this chapter use what's called a Bernoulli trial as kind of like the basis for how we determine if we use the model. Okay, so this is sort of like a what's the one or two, and a condition to check. We want to check to see if we're reading a particular problem. We want to read it and check, is this a Bernoulli trial? Because if something is a Bernoulli trial, what that means is that we can take that situation and apply it to one of these geometric or binomial situations. Okay, so a Bernoulli trial has three assumptions that have to be met. First of all, a Bernoulli trial, the possible outcomes are there's two possible outcomes. Okay, success and failure. And those two possible outcomes might be like, we flip a coin, it's a heads or it's a tails. Okay, two possible outcomes. So that's one of the three. There are three different sort of conditions that we can see if something is a Bernoulli trial. It has to have two possible outcomes. And those two possible outcomes can be A and not A, right? It could be like, if I'm drawing cards from a deck, I pull a heart or I don't pull a heart, right? That's Bernoulli trial because it's two possible outcomes. Or that part fits for this, to see if it's a Bernoulli trial. The second thing it needs to be, the probability of success, P, needs to remain constant. Okay, so everything that we've talked about with conditional probabilities takes it away from being a Bernoulli trial. Okay, the probability of success needs to stay constant. So again, flipping a coin, that is a good example of something that fits this, because the probability of flipping a heads is the same no matter how many heads I've drawn. But this is an example where card flipping probably, or pulling cards probably isn't great. If I pull a card and I don't put it back in the deck, I don't have a consistent probability of success. If it's pull a heart or not a heart, and on the first draw I pull a heart and then I set that card aside, the probability that I draw a heart is different now. So not Bernoulli trial at that point, because the probability of success would not be constant. So we need the probability of success to be constant. And then the third one is the trials are independent. So there can be no influence, right? The second trial has to be independent of the first trial. And that would be meaning that, so again, everything we learned about conditional probabilities, that takes that off the table because, those are dependent events. Okay? So a Bernoulli trial shows up if, if there's only two possible outcomes, the probability of success is constant, and the trials are independent. So as we read through our problems that have to do with this, we need to check these conditions, right? All three of these we need to check, and if they don't apply, then we cannot apply any of the models that we're using in this chapter. So this is kind of like I said, this is the basis for the probability models. We have to have these three conditions be true in order to use the techniques that we're learning in this chapter. So let's just talk a little practice with something as Bernoulli. Is flipping a coin and counting the heads a Bernoulli trial? So, one, is it, I already forgot what this thing was. Oh, is there only two possible outcomes? Heads and tails. Yes, that works. 2, is the probability of success constant? Yes, that works because it's always 0.5. 3, are they independent? Are coin flips independent of each other? Yes, they are independent. So, is this a Bernoulli trial? Yes, because those three conditions are met. I want to do one more of these together here, and then I want you guys to pause the video and do the rest on your notes and then come back to it. So, drawing cards without replacing them from a standard deck and counting the hearts drawn. Okay, so 1, is there 2 possible options? Hearts, not hearts. Yes, that works. 2, is the probability of success constant? No, there isn't, because without replacing them means that the second heart you draw, or the second card you draw, has a different probability than the first one. Therefore, the probability of success is not constant. That also means that they're not independent, because whether you draw a heart or not a heart is going to change the probability on the second draw. So we have 2 bads here, right? This is bad and this is bad. So is this a Bernoulli trial? No, it is not, because we have 2 different of the conditions being failed. Okay, pause the video now. Don't pause it right now. Like, you gotta hear the instructions first. So let me tell the instructions and then pause the video. What I want you to do is, on your notes, they have a bunch of these situations listed. I want you to go through and you can just decide, are these Bernoulli trials, okay? And then come back and we will, I'll just kind of go over each one quickly, okay? So pause the video now and do it, okay? Go. Okay, so theoretically, you paused the video and we're going to do these now, right? You've done them all? Okay, if you haven't, you should pause the video again so that you can do them. But I'm going to do it. I'm not going to play this game. So, determine the success of a marketed drug by looking at cases. So, number 1, is it 2 possible outcomes? Yes. It works or it doesn't work. Number 2, is the probability of success constant? Well, let's see. Is it the same for each one? That one's kind of hard to determine. For each person, would that probably be the same? Ooh, I don't know if we can say anything about that one. I'm going to say a tentative, maybe a no. 3rd, is it independent? Well, we have to make an assumption here that somebody's doing an appropriate field. So, this one could theoretically, if done correctly, could be a yes. If not done correctly, could be a no. So if you said yes or no to this one, you can actually make an argument either way on this one. Okay? If they did all the drug trials correctly, then theoretically it could be good, because the probability of success on one person should theoretically be the same for the next person. Whereas and if we would assume that if we're doing drug cases that somebody's going to use a proper placebo double-blind experiment to make sure that we have independence randomly assigned and all that stuff. So this one is technically a yes, but we could make an argument for no. All right. What about the next one? Removing M&Ms one at a time from bag to check if the bag fits the marketed 30% blue rate. Okay. So two possible outcomes. Yes, right? We have blue or not blue. Probability of success remaining constant. No, we don't. If we're taking M&Ms out of the bag, that means that every time we draw an M&M, we have a different probability of drawing a blue M&M. So that we do not have a constant success. So this one is a big fat no. The next one, drawing cards from a standard deck and replacing them and counting all the hearts, clubs, spades, and diamonds. Is it a two possible outcomes? No, this one does not have two possible outcomes because we're looking at hearts, clubs, spades, and diamonds. That's four possible outcomes. So this is a big fat no. Why does that one go up on top this time? That's weird. Finding the probability of missing 3 free throws in a row. So is it two possible outcomes? Yes, we have make it complement, doesn't make it. Is the probability of success constant? Theoretically, yes. I mean, if somebody has a 75% free throw rate, it tends to stick around 75%. So theoretically on this one, this is a yes. You might make the argument that with this and the second one that maybe there's a certain amount of pressure that comes that you make the first two and then you've got more pressure the third time. It's not a super strong argument, but you could technically make the argument there that the probabilities aren't constant. You'd probably be wrong, but you could make that argument. And that also the same goes for independence. Theoretically, yes, they should be independent, but maybe if I made the first two and I'm just a super nervous person, that third one's going to be harder because those two are dependent on the third one. So, I'm going to go ahead and call this one a yes. There's certainly some arguments that could be made to call it a no, but you probably would be wrong, like I said. Removing M&Ms from a bag, marking whether they are red or not, then placing them back in the bag. So, two possible outcomes. Yes, there's red or not red. Constant probability. Yes, because they are replacing them back in the bag. So there is a constant probability. And independence. I'm going to go ahead and say yes on this one. We should have independence. The next draw should not influence the other one. Because again, they're being placed back in the bag, so there shouldn't be anything going on. So this one is a yes, it is a Bernoulli trial. And that's it. Okay, so Bernoulli trials, the basis for these models. Let's talk about the geometric model today, and then we'll call it good. So, a single Bernoulli trial is usually not all that interesting. A geometric probability model tells us the probability for a random variable that counts the number of Bernoulli trials until the first success. That right there, the thing that is underlined, that is the key to determining if something is a geometric model. It counts the probability for a random variable that counts the number of Bernoulli trials until the first success. So we're looking for problems when we're reading this. If the problem states, how many times in a row can we get something correct before we get it wrong? Or how many free throws, what's the probability of getting 6 free throws in a row and then missing the 7th one? Or what's the probability that I'm pulling M&Ms from a bag, and the first 5, or the first one that isn't red, is the 6th one that I pull, okay? The phrasing of the question is going to help you determine if it's a geometric probability model. Geometric models are completely specified by one parameter, P. And that parameter P is the probability of success. And it is the way that we denote this is geom P. In fact, you have it on your calculator. There's a command for it. I think it's geomet P or PDF or CDF or something like that. We'll do calculator stuff on a day that I'm here, so don't worry about it. All right, so there is our formula for that. P of x equals x. This is the probability that the random variable equals a specific number, equals the probability of failure to the x minus 1 times the probability of success. And I want you to notice down here that the expected value and the standard deviation of the model have specific formulas. The expected value of a geometric model is 1 over the probability of success. And the standard deviation of a geometric model is the probability of failure over the probability of success squared, square root. There's a lot of formulas to memorize here. I want you guys to recognize that all of this stuff that you have here is on a formula sheet for the AP Stats test. You are given all of these formulas. There's no, as we go on here, you're going to recognize that we actually have a lot of formulas that come into play in this course, and that you are not required to memorize those. You are simply required to know what they are and what all of these things mean, right? So this is our geometric model. For Bernoulli Trials, let's do an example that uses it. So let's talk about coin flips. So coin flips, first of all, are they Bernoulli models? Bernoulli Trials, yes, it's heads or not heads. It has a probability of success that's constant, and the coin flips are independent. So what is the probability that the first heads is the 5th coin flip, right? So we use our model. This is going to be P of x equals 5, because they're saying this is what's the first one. The 5th one is the first heads. And what that equals is what I had in my formula from the last slide, which I'll just write up here real quick. Q to the x minus 1 times P. So this is Q to the 5 minus 1 times P. Well, let's get rid of the Q and the P. What is Q and P in this case? Probability of success, probability of failure, 0.5 times 0.5. So this is 0.5, blah, 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 0.5 to the 4th power times 0.5, which is really 0.5 to the 5th power, if we want to think about it. And then whatever 0.5 to the 5th power is. My calculator that I left up here by my board has suddenly disappeared. So I don't think I can calculate that for you this exact moment in time. It's nope, I got nothing. I can't do it. So so that whatever that is, that's my probability. It's 0.5 to the 5th. All right, I'm gonna go grab my calculator. Hold on. This is good video teaching because clearly we needed to waste these 15 seconds so I could grab my calculator. Let's actually do it. I feel like a jerk leaving no answer up there. This is 0.03125. So the probability that I'm gonna flip the coin, I get 4 tails and then a heads is 0.03125. There's a 3.125% chance that will happen. So the next question, on average, how many flips would you expect it to take to get a heads? I want you to recognize that that term that says on average means find the expected value, right? Find the average. which we saw in the last slide that the average for a geometric model is 1 over p. So therefore, this is 1 over 0.5, which is 2. So on average, we would need 2 flips to get a heads, which should make some sense, right? Because when I flip a coin, if I don't get a tail, if I get a heads on the first flip, then great, it only took me 1. But if I needed to, if I got a tails the second one, then it's going to be 2 flips. So on average, it should be right around there, like the 2 flips. We can calculate the standard deviation of that also. The standard deviation being the square root of p over q, no, it's q over p squared, which is square root of 0.5 over 0.5 squared. So let's calculate that. The square root of 0.5 divided by 0.5 squared is 1.41. So we have 2 flips as the average and 1.41 flips as the standard deviation. Alright, I think tomorrow we're going to do this spam example again. Or well, no, this is the first time you've seen the spam example. Sorry, I just did a whole bunch of these examples. So we're going to do this spam example as something we do in class. Hopefully. So that's it. I've got some problems for you to work on, and there we go.